Today, I will introduce a paper called CoT-VLA. It was presented at CVPR 2025 and written by researchers from NVIDIA, Stanford, and MIT. Let's get started. Before we begin today's paper, we need to understand the concept of VLA. A VLA generates an action based on both an image and a language instruction. And data consists of language instruction L, actions at each time step, and visual images at each time step. But this framework does not include a reasoning step, so it's difficult to execute more complex tasks. Traditionally, COT, the chain of thought method, is used to improve the performance of LLMs. Inspired by this idea, the CoT-VLA framework was introduced. Specifically, the framework creates subgoal images to support visual reasoning. This is the first contribution of the paper. Furthermore, the framework generates an action sequence, which is now called action chunk. And actionless data consists of language instructions and visual images at each time step. This is an example of executing. The video on the left shows the robot's actions, while the one on the right shows the predicted future images. Predict and move, predict and move. Based on this concept, let's look at the full architecture of CoT-VLA. First, the model receives the image and the instruction. Then it generates the predicted future image along with an action chunk. After that, the robot executes actions, and this cycle is repeated. Next, we'll look at the training. First of all, let's start with the backbone. As mentioned before, the model should be able to generate the two types of tokens, vision and action. So they choose VLA as the backbone. It's a unified multimodal foundation model that can both understand and generate image and text tokens. VLA converts image data into discrete visual tokens so it can align with text, and it can predict the next token for both text and image. We need to understand the part about discrete visual tokens first. Actually, image is continuous data and very large in size, so it's difficult to use transformers. Imagine generating an image of size 256 by 256 by 3 autoregressively. That's extremely difficult. Therefore, an efficient compression method is required. There was a method where an image is divided into patches. A famous example is VIT. However, since the embedding vectors are continuous, we couldn't directly use language models that operate on discrete tokens. To address this problem, vector quantization was introduced. The vectors obtained from patches are replaced with discrete indices from a codebook. As you can see in the left figure, the codebook is trained so that each entry can capture distinctive features of the patches, like this. However, as you might expect, replacing patches with codebook entries can lead to quality issues like the right figure. To address this problem, residual quantization was introduced. Residuals are divided into multiple depth levels and encoded sequentially in a coarse to fine manner. This allows for more precise patch representation and improves image generation quality. To efficiently learn this residual quantization process, the depth transformer was introduced. The role of the depth transformer is to regressively predict the residual codes at each depth for every patch. Now let's go back to the paper and take a look at the visual token prediction. For subgoal image generation, each training sequence is constructed in the form like this. At each visual position j, we take the embedding hj generated by LLM as input. Then the depth transformer p autoregressively predicts the residual tokens um, from kj1 up to kjd. The training objective for visual tokens is formulated as negative log likelihood shown in the equation here. To make this possible, causal attention is applied so that each visual token is predicted sequentially. This means the model follows the next token prediction approach. It only looks at the previous tokens when predicting the next one. For action token prediction, we need the language instruction L, the visual images S, and the action chunk A. Each action is represented as a 7-dimensional vector. Since robot joints are usually continuous values, these also need to be discretized. So each dimension is quantized into 256 bins and finally represented as 7 tokens. Interestingly, these 256 tokens are reused from the text vocabulary, specifically the ones that are rarely used. Now, as you can see in the figure, when generating one action, the model also refers to the other action, like this. This allows it to capture the interactions across different joints. Finally, during sequence training, the entire action chunk is generated at once, which enables parallel prediction. This hybrid attention mechanism for learning both images and actions is the second contribution of this paper. The last contribution is that the authors conducted extensive experiments in both simulation environments such as Libero and Bridge V2 and in the real-world robot environment, Franca tabletop. In fact, CoT-VLA achieved state-of-the-art performance across multiple benchmarks, both in simulation and in the real world. Here you can see the results on the Franca tabletop benchmarks, and for other benchmarks, the detailed results are available on the website. Now, let's look at the impact of pre-training, visual chain of thought, and hybrid attention. These components significantly improve test performance. With them, the model can better understand complex tasks, and it can also predict actions in a more stable and accurate way. Next, Let's talk about the generalization ability of visual reasoning and how it contributes to action prediction. With stronger visual reasoning, the model can generate more accurate action sequences even in unseen situations and environments. This effect is specifically clear in tasks that require complex visual reasoning, where we see a significant improvement in action performance. Thank you for listening.